Yeah. John?
Hey.
Yes. Sorry, we had the wrong link. Yeah.
Sorry for the delay.
Okay.
Yeah.
Guess we can start.
Yeah.
With recording already. Okay.
Someone
Hello.
want to Corentin? Yeah. You want to introduce Corentin?
Okay. Okay. So Corentin, welcome.
Yes.
Well,
Thank you.
yeah.
We are yes. So
Yeah. Sorry, we had the wrong link just now.
Sorry, we
All
were
right.
in another Zoom meeting, but we are more people here in the room. You just cannot see all
I
of
see.
us.
yeah.
Okay, good. Should I share my screen? Do you guys hear me okay? Yes? Okay.
Yes.
Let me just share my slides.
Yeah, we can. Yeah,
Mhm.
yeah, we can see. Yeah. See the presentation.
Okay.
Yeah.
Maybe just minimize this a little bit.
Okay. So it's our pleasure. Actually, Corentin, you're the first one to go fully like online. Normally we had speakers here, but it's a pleasure to have to go really international. So Corentin will talk to us about on the secret distribution module learning with errors. So thank you very much. The floor is yours.
Thank you. Thank you so much for the introduction, and once again, thank you for giving me this opportunity to present my work, even if it's remotely. It's always nice to be able to present to a larger crowd of people. So today I want to talk to you about the secret distribution of in the module learning with errors problem, which is one of the core assumption in lattice-based cryptography and more generally in post-quantum cryptography. So this talk is composed of different works that we did with Katharina Boudgouste, Adeline Roulanglois, and Wei-Chong Wen over a couple of years, and I tried to condense it to this specific talk and try to look at the different choices of secret distributions that we can choose in this problem. And I'm going to define all of it in the talk so that it's more clear. So first, let's start with a quick word on post-quantum cryptography. The security of currently deployed public key crypto systems is heavily relying on two assumptions, which is factoring for factoring large numbers in the product of primes, and the discrete logarithm problems in cyclic groups. But with the recent advances in quantum computing, the natural question to ask is, what if we had a powerful quantum computer? Should we reassess those assumptions? Should we reassess the security of our cryptography or of our public key cryptography today? And the answer is yes, unfortunately, because Peter Shor in 1994 proposed an algorithm that solves both factoring and discrete log in polynomial time. So it provides an exponential quantum speedup as opposed to what we know right now using our classical computer, where our best algorithms are exponentially complex. So here, it would be able to solve it in polynomial time, meaning that the hardness assumptions that underlie, let's say, RSA and elliptic curve cryptography, so all of the public key crypto deployed today, those assumptions would no longer be valid in a quantum world. So we need to provide new assumptions and design new crypto systems based on these assumptions. Those mathematical problems should be hard, even quantumly. So they should withstand those quantum algorithms that might be invented in the future. One thing that I want to mention, and that is always mentioned when talking about post-quantum cryptography, is that we need to do this fast. We need to do this right now, because an adversary could store ciphertext encrypted with RSA, for example. It could do so today, wait until a quantum computer is built, and then decrypt it using Shor's algorithm at a future point in time. But if this future point in time is close enough so that the data encrypted is still sensitive, then this could cause security issues. So we need to really anticipate those threats and move this transition right now, have this transition right now to post-quantum cryptography. And this is what NIST has been doing for the past few years. They have launched a post-quantum standardization effort back in 2016. And in July last year, they announced the first round of standardized algorithms. So for encryption or key encapsulation mechanisms, we have Crystal's Kyber. And for signature schemes, we have Crystal's Dilithium, Falcon, and Sphinx Plus. The ones that I highlighted in orange are based on lattices, so are part of lattice-based cryptography, which I'm going to talk about in a second. And the first two, Kyber and Dilithium, are directly based on the hardness of the modulo learning with errors problem, which is the one that I want to focus on in this talk. And one thing that is even more pressing is that NSA has already announced its NSA Suite 2.0 for quantum-resistant cryptography, and it includes Kyber and Dilithium. So it means that Kyber and Dilithium will be used for national security protection, which means that we really need to be careful about the underlying assumptions, and in particular, modulo M-LWE. So this is what I want to focus on today, is to assess whether M-LWE satisfied basic security requirements for Kyber and Dilithium to be secure, and especially because Kyber and Dilithium use very specific choices for the secret distribution. And we need to focus on this parameter and whether the M-LWE problem is robust with these distribution to ensure a minimum level of security. Okay, so now I want to introduce the problem by starting with lattices, because I've said the word lattice a little bit too many times without even defining it. Then I'm going to define the LWE problem, which is the original problem, the original formulation. And then we're going to move to modulo learning with errors before starting with all the hardness proofs. Okay, so what is a lattice? A lattice is a discrete subgroup of the Euclidean space, which is a rather fancy way of saying that it is a periodic grid of points in n dimensions. And each lattice, can be described by a multitude of bases, which are on the right-hand side here are in blue or in orange. And a lattice will be the set of integral linear combinations of those basis vectors. So it gives this all of these black points on the picture on the right. And so I have two examples of bases. I have one in blue, which is rather short and has highly orthogonal vectors. And on the contrary, I have another basis in orange, which is composed of longer vectors and that are almost collinear. So depending on the basis I'm going to be given, I can already see that it might be a whole other situation to solve the lattice problems. And one of the lattice problems that I want to consider is the closest vector problem, the CVP. So given a lattice, which is described by a basis, either the blue one or the orange one, and given a target T, which is a vector in the ambient space, my question is to find the closest lattice point to T. So I want to find the lattice point X, which minimizes the distance X minus T. And so based on the lattice basis I'm given, then if I'm in several hundreds of dimensions, if I have a short basis with highly orthogonal vectors, then this problem might be easy, and it actually is. But if I'm given a basis rather like the one in orange, composed of really long vectors and collinear vectors or almost collinear, then my problem will become exponentially hard. And this is the whole foundation of lattice-based cryptography. Now, this CVP problem is instantiated with a lattice. I take a lattice, I give you a basis, and you have to solve this problem. But we have to determine which kind of lattice we want to provide the adversary with and which instance to consider. And in lattice-based crypto, what we use are generally random lattices. So in random lattices, we take a matrix A, which is random over ZQ and of size m by d, and I consider the lattice LQ of A, which is the set of integral vectors x, which can be written as A times S mod Q for certain vector S. So now I have the lattice that I want to solve CVP on. And now let me define my target. So my target, I'm going to take a lattice point, A times S, and I'm going to perturb it by a small amount, by an error E. So this gives me my target AS plus E. And I ask you to solve CVP with this target and on the lattice LQ of A. And what I'm saying is that this is exactly solving LWE. So if you can solve CVP with this target on this lattice, this is exactly the LWE problem. So this is a rather nice geometric way of interpreting LWE as a lattice problem and make the link with lattice-based crypto. But generally, we use a more linear algebraic definition. So in this definition, I give you a matrix A, uniformly random over ZQ. This defines my lattice, and I generate my target T as A times S plus E, as before, where S is drawn from a secret distribution, and E is drawn from a short, typically Gaussian distribution. And now my search LWE problem is to solve this noisy linear system. Given A and T, I ask you to find the vector S. So what's interesting about this problem is that in public key crypto systems relying on LWE, the public key are A and T, and the secret key is the vector S. And so solving the LWE problem is exactly performing a key recovery attack. So if the search LWE problem is hard, then it should be infeasible to recover the secret key from the public key. So this is one of the basic security requirements that we expect. Now, you can also have a decisional variant of the problem, which is a little bit more interesting and a little bit more general. And the decision problem goes as follows. I give you some A and some T, and I ask you to decide whether T was generated as before, as A times S plus E, or if it was just sampled uniformly at random. So this gives me a decision problem, which I'm going to use to be able to prove that certain encryption schemes are secure and construct several cryptographic primitives from it. So it's slightly more interesting. Now, what I didn't mention just yet is the choice of this secret distribution. For the error distribution, I said we take a Gaussian, and it's really important to have an error, because if I don't have an error, then from A times S, I can just use linear algebra to solve for S. But now I have a Gaussian error, so this algebraic attack doesn't work anymore. But if I don't choose this secret distribution properly, then the problem might still be easy to solve. So the original formulation, which I call standard secret, introduced by Rigef in 2005, chooses the secret distribution as just the uniform distribution over all ZQ. So this gives a nice problem, which has worst case to average case reduction from those CVP and SVP problems on lattices. So this is very interesting, but it gives rather intractable parameters. So to optimize a little bit the efficiency, we can consider a binary secret version, which was introduced first by Goldwasser and co-authors in 2010 and improved by Braksky, Langlois, Pikert, Rigef, and Stille. And so here, the distribution of secrets is the uniform distribution, but over just binary vectors. So this is an alternative. And there is also a more recent series of works started by Braksky and Dotling, which assess the hardness of the problem when the secret distribution does not have any assumption on it, except that it has a certain amount of entropy. So this is a rather parallel way, parallel research direction. So I'm going to mention it because I want to talk about this result in modules, but it should be differentiated from the, say, binary secret version. Okay, so as I mentioned, you have intractable key sizes and parameter sizes for standard secret, but even in the case of binary secret, when you reduce the size of the secret, you still have matrices in very large dimensions. So D is typically your security parameter because it's the dimension of your secret. M is usually D log Q, and Q is usually 2 to the 13 or 2 to the 23, for example, in the case of dilithium. So it leads to very high dimensional problems and very high dimensional parameters for crypto systems, which turns out to be quite inefficient. So to improve this efficiency, the idea is to add some algebraic structure within the problem. And this algebraic structure that we're going to introduce is designed to drastically reduce the amount of storage that we need for matrices. So on this picture, you can see that on the left-hand side, I have a matrix which is depicted as fully random. It has those fully random entries. And by adding this structure, I'm going to have a matrix that has these blocks, which are, say, random between them and independent between them. But among one block, I have this very specific diagonal structure, which I'm going to leverage to speed up computations and reduce the amount of storage that I need. So the idea of this structure, of this algebraic structure, is to replace the set of integers, Z, by some elements of a more general ring, R, which is the ring of polynomial with integer coefficients, and a quotient by some polynomial f. So you can think of a power of 2 cyclotomic ring, which in this case would be f of x equals xn plus 1, where n is a power of 2. And so this gives you a ring where your elements are essentially integer polynomials of degree less or equal than n minus 1, essentially. And since I work over ZQ for my LWE problem, I'm also going to work over RQ, where I reduce all the coefficients of my ring elements by Q. Yeah. Okay, so now I have elements in my ring R, and I have several ways of interpreting those. The first and more natural one is to see this polynomials as its vector of coefficients. So I use what we call coefficient embedding, and I can represent my polynomial, my ring element, with a vector of n integers. The second representation, which is going to be more important when looking at storage optimization, is when it comes to multiplying two ring elements together. This multiplication in the ring translates into a matrix vector product in the coefficients. So I have a matrix of size n by n, which is determined by the polynomial a, and I have the vector of coefficients of the polynomial b. But this matrix of size n by n is not just fully random. It has this specific structure, this tuplet structure, which means that, first of all, I'm going to be able to perform this matrix vector product more efficiently. And also, because of this structure, in order to store the entire n by n matrix, I don't need n squared coefficient, but I only need n. And the reason for why it is because this matrix is fully determined by the polynomial a, which itself is fully determined by its coefficient vector. So in the end, to store this n by n matrix, I only need n integers once again. So this gives you a grasp for why representing matrices with this structure will allow us to reduce the amount of storage that we need for matrices. And we'll see in the next slide why this is interesting. And in terms of efficiency, as I said, you can leverage this structure to perform the product more efficiently. But if you look at the multiplication directly in the ring, you can also use like FFT algorithms to perform the multiplication quite efficiently. So all this algebraic structure does is basically optimizing the efficiency of your scheme and of your problem. So now we need to consider the problem and assess the security, which is kind of the downside of adding this structure. But now that we have this structure in mind, while the module learning with errors problem is not very different from the LWE problem that I presented before. I still have a matrix A, which is now uniformly random over RQ. And I have my target T as AS plus E. And my search M-LWE problem still asks to find S given A and T. And I can, once again, tweak the secret distribution of S to have different variants of the problem. I also have a decision problem, which is the same as before, which is to distinguish T equals AS plus E from a T that is uniformly random over RQ. And so to just give a little bit more intuition on why we gain storage, when I use my 2 representation of my ring elements for this problem, since I multiply by my matrix A, I'm going to have to store all of these multiplication matrix, those tuplets matrices. And for the vector S and E, I can just use the concatenation of those coefficient vectors. But now I'm again over the integers, so we could think that it's the same as LWE, but if you look more closely, the matrix A is over the integers, but it has these blocks which have structure within them. So this is not exactly LWE because the matrix A is not perfectly random, but it has this structure, so it can be seen as kind of a structured variant of LWE. And this is usually what we do to evaluate the parameters that we need for our crypto systems. We just use this structured variant and essentially say it's the same as LWE. But when we look at the theoretical hardness, this structure gives us a little bit of a hard time when trying to prove the hardness of the problem. And this is what I'm going to try to explain in the remaining time that I have for this talk, is how we can prove the hardness for different choices of secret distributions for this M-LWE problem. But first, what do we know about those different choices? For LWE, we know that we can choose standard secret or binary secrets or arbitrary secret with certain entropy. But for M-LWE, we don't know much, at least not prior to our works. So the only result that we know is by M-LWE and Steele from 2015, which introduces M-LWE and kind of translates what Regev did in 2005 to the module setting. And what I want to present today is several contributions that were designed to fill all these gaps and have a better understanding of the hardness of M-LWE depending on the choice of the secret distribution. So I want to focus on 3 of these contributions, which are the hardness of the search and decision variant of M-LWE with short binary secrets. So by binary, I mean binary polynomials this time. And the third one is the search hardness of M-LWE with an arbitrary secret, provided that it has sufficient entropy. And there is already a work by Lin Wang and Wang from 2020, which does the same, but I want to look at it in a different way, and I'm going to explain it a little bit later on. Okay, so now we're ready to dive into the main core of this talk, which are the hardness proofs. Now we understand what the problem is, and we try to see which distribution we can plug into the problem while proving its hardness. So first, I want to provide the hardness with short, like binary secrets for both the search variant and the decision variant. Okay, so for the search variant, we start with A and AZ plus E, where Z is a short binary vector. And I want to show that it's hard to recover Z given these elements. This is the definition of the problem. And so to do that, what I assume is that M-LWE with standard secret is a hard problem. This is what was proven by Lengo and Steele in 2015. So I can make this assumption and try to link this assumption to the one that I'm trying to prove the hardness of. So my first step is a quite standard step, which we're going to find again in the next reductions as well, is a lossy argument, which essentially replaces the matrix A by some BC plus N, where B and C are uniform matrices over R mod Q, and N is a short Gaussian matrix. And this should be reminiscent of M-LWE, where we could see B as my public matrix, C as my secret matrix, and N as my error matrix, because it's from a Gaussian. But I have this matrix formulation instead of vectors, but by using a hybrid argument, I can actually prove that it also relies on the standard M-LWE problem. So now I have this multiple secret M-LWE assumption. And what I'm saying is that an adversary will not have a significantly larger advantage in finding Z in the second situation than it did in the first situation, because my multiple secret M-LWE is assumed to be a hard problem. So now I have decomposed my matrix A to BC plus N. So in the second term, I get BCZ plus NZ plus E. And now I want to do the remainder of this reduction in 2 steps. The first thing is looking at the error, which is E, a Gaussian vector, plus some N times Z. And N is a Gaussian matrix, so it's short, and Z is a short binary vector. But since my vector is short, since my vector is the secret, I cannot directly say that this is an error vector, and so I directly have M-LWE, because my error depends on my secret. So it's kind of a tricky situation. But by observing that N and Z are short, then N times Z is short, then my error here looks like a Gaussian distribution with which is E, with a shifted center, which is N times Z. And what I'm saying is that if my Gaussian standard deviation is large enough with respect to N times Z, then it might completely drown the fact that my Gaussian is uncentered. And you can do this by using statistical arguments, but by using the statistical distance, you're going to end up with parameters that a Gaussian parameters that needs to be super polynomial, a super polynomial factor times the norm of N times Z, which will lead in super polynomial parameters, which gives you intractable key sizes and intractable parameters. So instead, what we use is an improved noise flooding argument using the Rennes divergence, which is much more compact. And essentially what we end up with is that the Gaussian parameter of E must just be larger than the norm of N times Z, so which stays polynomial. And so now we can replace this N times Z plus E by some Gaussian vector F, which does not depend on the secret anymore. Now, finally, I have this C times Z, and I want to interpret that as a standard secret. And this argument is that C is defines a universal hash function if my dimensions are well chosen. So if K, the number of rows in C, and the number of columns is sufficiently larger than K, then I can argue that by the leftover hash lemma, C times Z will be indistinguishable from a uniform vector S over R mod Q. And so now I have this BS plus F, which is essentially M-LWE with standard secret. So the adversary will not have a good advantage in solving this problem based on my M-LWE assumption, which means that if I go back to all those steps, then finding Z given A and AZ plus E will be a hard problem as well. So this was the main argument for this search hardness of M-LWE with short secret. And now I want to argue that this actually doesn't work for decision. And the reason for that is because of this Rennes divergence argument. The Rennes divergence is very well suited for search problems, but not so much for decisional problems. And so here, since we can't use the Rennes divergence, we could be tempted in using the statistical distance. But as I said, the statistical distance would lead to intractable parameters. So I need to find another way of getting rid of this N times Z, which is essentially the whole bottleneck of this noise flooding argument. So for the decision problem, what I want to say is that if I give the adversary n times z, then I don't have to mask in any way that this Gaussian error is uncentered, because I just give n times z, so I don't care if it leaks the information to the adversary because it already has it. And so this is why the pseudo-randomness of M-LWE, so the decision variant, is a little bit trickier. The idea is that I want to give the adversary n times z in addition to what he had before. And I want to prove that this still gives me a hard problem. So I start with M-LWE, and I'm going to start giving some more hints to the adversary and trying to see what I can adjust in the parameters to keep a hard problem. The first step is to just give, in addition to A and AS plus E, I give the first coefficient of the error. So I end up with a problem, which is called first is errorless, M-LWE. And it should be easier, but if I increase the rank by just 1, then this actually is slightly harder than M-LWE itself. And now I want to generalize this hint. And instead of just giving this inner product between E and the first canonical vector, I'm going to give the inner product between E and a short binary polynomial vector, Z. So this gives me an extended M-LWE problem, which is a new assumption. And if I increase the width of my Gaussian error E, then I can keep the hardness pretty much as it was before. And then I'm going to use a hybrid argument to go to a matrix version of this problem, a multiple secret version of this problem. And so I have an error matrix now, so not just one vector E. And my error matrix, this hint, which was the inner product, turns into a matrix vector product n times z. And this is what I wanted, because now I have an assumption in which I give the adversary n times z, and this is still proven to be hard under the M-LWE assumption. And so now I'm going to go back to my previous picture, which is the final arrow here, and try to use this assumption to have the decisional hardness of M-LWE. So I start again with A and AZ plus E. And now I'm first going to decompose the error E into negative n times z plus f, where f and n are Gaussian elements, and f is a Gaussian independent of z. So depending on the parameters, I can tweak those a little bit to make it work. And now I'm going to once again use my lossy argument, and I'm going to use my multiple secret variant to replace A by BC plus n. But this time, since in the second term I already introduced n times z, then the adversary might have some information about n times z. So I need to include this into my assumption, and this was the whole purpose of this extended M-LWE assumption, because it doesn't matter now if I give n times z to the adversary. So based on this new assumption, I can do this replacement, and this will cancel out the negative n times z that I introduced before. And now I end up with something that has an error that no longer depends on the secret. And now I can just use the same argument as I did before. So I'm going to use the leftover hash lemma to replace c times z by some uniform vector s. And then I end up with this bs plus f, which is M-LWE. And so based on the decisional variant of M-LWE this time, this should be indistinguishable from a uniform vector t. So I replace bs plus f by a uniform t, and then I replace again this a hat, which was bc plus n, by a uniform matrix A using the same argument as before. And by using this extended M-LWE, I managed with this chain of indistinguishability, I managed to prove that A and AZ plus E for a short vector Z is indistinguishable from A and T, where T is uniform. So this gives me the hardness of the decisional variant. Okay. Feel free to interrupt me if you have any questions, but otherwise I'm going to keep going. So To sum up these two reductions, what it is giving is a reduction from standard M-LWE, so with secret, uniform, and RQ, to a short secret variant where the secret is uniform over binary polynomials. I'm not going to enter into the details of all these parameter constraints. The main takeaways are that the first contribution is only for the surge variant because of the Rennes divergence, while the second one is more general because it tackles the decision variant. And the other thing that is more problematic is that because of this leftover hash lemma, as I mentioned, the matrix C must have dimensions that allow us to use the leftover hash lemma. And for that matrix to be a universal hash function, it means that we need to take the rank D to be at least K log Q. So K is the starting rank, which is say 1 or 2, but log Q can be very large. So in the case of dilithium, it's 23. So it means that D will be of size about 23 or 46, something like this. So it's quite impractical for public key crypto systems.
I have a question.
Yes.
So that's because you use the green leftover hash lemma, really?
I'm sorry, I didn't hear. Can you repeat
that's
the
the
question?
leftover hash lemma over the greens, right? That's why you have the red K over there.
Yes. Yes. So yeah, the leftover hash lemma essentially say that your secret must have sufficient entropy and that that your hash function should have dimensions so that it's lossy enough so that it loses enough information about S by performing the hash of this S. So this is why you need this K log Q. And the difference between the, yes?
But this is not only the entropy requirement, right? This is also the ring structure we are.
Yes. Yes, you also have the ring structure, but those conditions actually come up even in the standard LWE case.
Yeah, sure.
Yeah.
Okay, sorry.
So yeah, this is the main bottleneck, is that since we need to use the leftover hash lemma in those proof structure, we inherently suffer from this large rank of K log Q. So I have two questions which arise from these two reductions. The first one is, so far we only looked at uniform secrets, so uniform over binary polynomials. And we also have this rank restriction, as you mentioned, of K log Q. And so can we have a hardness result for smaller rank and one that does not increase the rank throughout the reduction? This would be the goal. And this is why I want to focus now on a second part of our contributions, which was on this arbitrary secret variant of M-LWE, and where we don't assume anything about the secret distribution, so not necessarily uniform anymore. And we want to prove it using a rank preserving reduction, meaning that we don't have to increase the rank within the reduction. The reason why we are interested in this non-uniform secret or this arbitrary secret case is motivated by the leakage resilience of M-LWE-based crypto systems. And let me give you an intuition why. Assume that I have an attacker that is allowed to perform physical attacks and recover some noisy version of the secret, S tilde, which is S plus some S prime, where S prime is a random perturbation, is composed of random bit flips, for example, due to the hardware, but it has a much lower entropy than S used to have. So now they can target a new M-LWE instance by computing delta T, which is AS tilde minus T, which is A times S prime minus E. So this M-LWE instance is with a secret S prime that has a much lower entropy than S, and since it comes from like typically the hardware and the physical property of the attack, then you cannot necessarily assume anything about the form of the distribution of S prime. And in particular, you can't assume that it's uniform binary or something else. So now the question that arises is, under what condition on S prime can I still prove the problem to be hard? And my intuition is that if S prime has enough entropy to begin with, if it's random enough to begin with, then the problem might still be a hard problem. And this relies on this intuition of lossiness. And this is actually the proof idea that I want to convey here, is that I want to show that this conditional entropy at the bottom, the entropy of S prime given A and AS prime plus E, is large. And what I'm saying is that if this is large, then M-LWE with secret S prime should be a hard problem. And the intuition behind it is because given A and yes?
Question.
Yeah. Can you briefly explain the cold boot attack?
So the cold boot attack, essentially, your secret S is your long-term secret key, so it's gonna have to be stored in RAM at some point when you want to perform decryption or signature in the case of dilithium. So you're gonna have to store this element in RAM, in random access memory, and so you know that the data that is stored in RAM should be volatile in the sense that it should be erased once it's not used. But the cold boot attack essentially is leveraging the physical property of this random access memory to recover some information about the secret. And typically, the idea of cold boot attacks is to lower the temperature of the physical component, the physical RAM, so that this volatility of the secret S is longer. So it means that this long-term secret key stays longer in RAM, which allows the attacker to have more time to recover this S prime. Now, this is a physical attack, so it means that the adversary needs to have physical access to the crypto component that performs the operations. So this is a weird setting, but this is the idea of the attack. And the thing that this random perturbation, this S prime, actually comes from the fact that the longer you stay, even though it's low temperature, you're gonna introduce more and more errors as time goes by, and more random bit flips and random perturbation to the original secret S. So you're gonna have this S plus S prime. Does that answer your question?
Yes, yeah, thank you. That's great.
Yeah, okay. Okay, so back to this lossiness thing. What I want to say is that the function that maps S prime to AS prime plus E loses enough information on S prime for it to be recovered. So it means that giving you A and AS prime plus E shouldn't give you too much information to recover S prime. So this is exactly what I want to encapsulate with this conditional entropy. Now, for the second question about, if you remember on the previous slide, I wanted to have a rank preserving reduction to not have this leftover hash lemma and this log Q blow up in my reduction. And for that, I won't be able to use the same argument as before, because otherwise I'm going to encounter the same problems. So I'm going to use a different assumption, which is modulo n-true. So for those of you who are familiar with first the n-true assumption, it states that a uniform polynomial over RQ, A, is indistinguishable from a ratio of short, typically Gaussian polynomial F and G. So I write this ratio as G times FQ inverse, where FQ inverse is the inverse of F, but in RQ. So the inverse mod Q. Now, from this n-true problem, I can consider a more relaxed variant, which is called n-true learning, where I have a vector A, uniformly random, and I say that this is indistinguishable from G times FQ inverse again, but I use the same denominator F. So it's not exactly packing several untrue instances in a single vector. It's actually a new assumption. And if the width of the Gaussian are not too small, and if the dimension M is not too big, then this untrue learning problem is not significantly easier than untrue itself. And so from this generalization, from this untrue learning, I can obtain a matrix variant, which I call modulo untrue, where you have a uniform matrix A, and you say that this is indistinguishable from this G times FQ inverse, where G is now a matrix, and FQ inverse is an invertible, so the inverse of an invertible square matrix. So you have this kind of ratio of matrices appearing here. And now we're going to use this assumption in our lossy argument. So now I want to prove the hardness of M-LWE, where I don't assume anything about the distribution of the secret, except that it has a certain amount of randomness, of entropy. And in the end, what I want is to determine the threshold of entropy above which the problem stays hard. Okay? So I start with AS plus E once again, and I use my lossy argument, but this time I don't replace A by BC plus N, but I use my modulo untrue assumption and replace A by G times FQ inverse. So if modulo untrue is hard, then the adversary should not have a significantly larger advantage in finding S in this situation. Now I'm going to decompose the error E, which is a continuous Gaussian. I'm going to decompose it into G times F inverse times E1 plus E prime 1. And based on, so all of these are Gaussians. And if I tweak the Gaussian parameters correctly, then I can do this decomposition. This is going to give me some restrictions, but I can do this decomposition. Okay, so now I can factor G out, and I end up with this big expression at the top. And now this is where I'm going to have my lossiness argument, in which I want to prove that the entropy of S, given this big expression at the top, I want to prove that this lossiness is large enough, because this means that my expression has lost enough information on S for it to be recovered entirely. Okay? So I'm going to skip the details of all these inequalities. You can find the details in the papers if you're interested. But what we end up proving is that this lossiness is larger than the entropy of S. This is good because this is the only thing that we know. The entropy of S minus something else, let's call it K. And so what I'm saying is that this is my entropy threshold, because if H of S is equal to K plus something super logarithmic in the security parameter, then it says that my lossiness at the top is super logarithmic in my security parameter. So it is large enough to guarantee the hardness of the problem, meaning that my expression lost enough information on S to recover, for an adversary to recover S. And if we go back to the first step, then it means that it's hard to recover S given A and AS plus E. Okay, so we have two quantities here, those two norms of matrices, which are singular values of random Gaussian matrices over the ring. And part of our work was also to try and optimize those values, so to have probabilistic bounds on these values as tight as possible to have the best, the tightest reduction and the best parameters overall. Because if I can minimize the norm of F, then I have a better entropy condition, so I can reach lower entropy secrets. And if I minimize the norm of G times F inverse, then I'm gonna reduce the blow up factor that I need for my Gaussian error for the reduction to go through, and this will give me better parameters overall. One thing that you can already notice here from this entropy condition is that it is already quite substantial, and in particular, it means that you cannot reach arbitrarily small secrets. Typically, you cannot reach binary secrets, but it's even more restrictive than that. You cannot reach like constant size secrets. So you're going to be able to have distributions that are in between the short uniform distribution and the large standard secret distribution, but not all of them because of this entropy requirement. Okay, so this is pretty much it for this for all these reduction proofs. I hope this was not too technical, but also technical enough for it to be interesting. And so to wrap things up, what we provided in all these works was to prove the hardness, the theoretical hardness of one of the main assumptions in lattice-based crypto, with closer and closer, while getting closer and closer to practical parameters. So we're not quite there yet, because in the first two reductions, we end up with short binary secrets, which is good, which is what is used in practice, but we have those rank conditions, which means that your problem is only secure if you choose like a rank of 23 or 46, and typical parameters use more like 4 to 7. So it's quite of a gap that we still need to reduce, but it's making a step towards narrowing this gap. And the second results based on modulo and true that I presented, it gives us sufficient condition on the secret distribution for the M-LWE system to be leakage resilient, meaning that even if an adversary can perform these physical attacks or recover some noisy version of the secret, then it cannot directly solve the problem entirely, cannot break the entire system. For this second work on the entropic secret, I mentioned a previous work from Min Wang and Wang from 2020, which does roughly the same thing, but they start from modulo LWE. And so inherently, they suffer from the same problem that we had, which is the rank increase in the reduction. So they don't have a rank preserving reduction. And yeah, so they start from a better understood assumption, which is modulo LWE, but they don't have this rank preserving. And depending on the use case, you have better or worse parameters. So depending on the use case, you're going to have to use either our reduction or theirs. It really depends. But regardless, all of these results, once again, are limited to either reducing the size of the secret, but at the expense of the rank, or keeping the rank small, but at the expense of larger entropy secrets. And so one of the main open question that is still present after all of this is whether we can prove the hardness of modulo LWE with very low entropy secrets, like binary secrets or ternary secrets, but without having to increase the rank too much to keep a rank that is practical and that we can use, say, for designing encryption or signatures. So yeah, this is the main bottleneck and the main research question that I want to convey outside of all of these, in the end of all of these works. And we still don't have any clue on how to prove it, either for modulo LWE, but also for LWE without this algebraic structure. So this would be very interesting to have ideas in order to do so. Yeah. And that's it for me. So I hope this was understandable. Thank you for your attention, and feel free if you have any further questions. Thank you so much.
Yeah, thank you. Okay, thank you. So I have a question. So what about the small error case?
Okay, yeah. So in our latest paper that has been published in the Journal of Crypto, I think in January 2023, so January this year, we looked at the hardness of M-LWE with binary errors, so uniform binary. And you have a different kind of proof technique, which in the end proves that you cannot have too many samples within your matrix. So you cannot have a matrix A that has too many rows, because otherwise you can have algebraic attacks, which essentially break your system. And so we managed to have those results for binary error, or actually ADA bounded error, but with further restrictions on the number of samples that you give. I'm going to anticipate maybe one question that we get asked a lot based on all those results, is whether we can have an entropic version of M-LWE for the error part. And so it means that we don't assume anything about the form of the distribution of error, just as that it has a certain amount of entropy. And this is a little bit more tricky than the secret part, because typically, if I take an example of an error vector that is very sparse, so it has a lot of zeros and all of its entropy lies, say, in its first couple of coefficients, then you can also have algebraic attacks. So the size of your error coefficients is actually not the bottleneck with respect to algebraic attacks. It's more the sparsity of your vector. So if we want to have such an entropic error result, we would have also conditions on the sparsity of the vector. And the reason why we don't have that for the entropic secret that I presented before is because the matrix A multiplies to the vector X and essentially comes and scrambles all of this sparsity issues and completely like uniformize this the entropy of the secret into like uniformly into a vector. But since you don't multiply the error by anything, you can't have this shuffling of the entropy, and so you don't have a vector that is where you can just assume that it has a certain amount of entropy just based on the sparsity issues that I mentioned.
Okay, thank you.
More questions from the audience?
Oh, I don't know if there are questions in the chat. No, I think not. Yeah. I always forgot to look at the chat.
If no more questions, then let's thank Corentin again. Thank you very much for this very nice talk.
Thank you. Thank you. Thank you for the invitation. It was very nice. Yeah.
Thank you.
Then, so in 2 weeks, we're going to have another talk again on lattices by David Wu. So join us in 2 weeks if you are interested. So thank you again.
Yeah, for sure.
Have a good day, everyone.
Thank you.
Okay,
Thank you so much.
Okay, thank you. Bye bye.
Bye.
Thank you. Bye.